Welcome back to Mechanical Engineering Made Simple.
It's great to be back. And today, we're doing something a little different. We're sort of stepping away from the shop floor for a bit.
We really are. You know, when people think about mechanical engineering, the image that usually comes to mind is very physical, very tangible.
Oh, absolutely. You think of a wrench, a lathe, maybe a big schematic rolled out on a drafting table.
Exactly. The smell of machine oil and metal filings. It's all about the hardware, the stuff you can touch and hold. But today, we're putting all that aside.
We are. We're moving beyond the drafting board, beyond the wrench, and into the digital realm.
We're doing a deep dive into the digital revolution that completely, and I mean completely, changed how things get made. This isn't just about new tools, it's about a new way of thinking.
It really is. We're looking at the whole ecosystem, from the philosophy of how teams even work together, all the way to these incredible virtual worlds where products get tested before a single atom of them exists in reality.
It sounds like science fiction, but it's the day-to-day reality for engineers now. And to guide us, we're analyzing a specific stack of research that really breaks this down into 4 key pillars.
Right. The first one is the philosophy itself. It's called concurrent engineering, or CE. It's basically the story of how engineers stopped working in isolated silos.
That famous over-the-wall approach, we'll get into that.
Then we have the technologies that made it all possible, the digital glue, if you will. Things we take for granted now, like email and shared databases, but were revolutionary at the time.
And from there, we move to the digital canvas itself, computer-aided design, or CAD, how we went from drawing lines to building intelligent 3D models.
And finally, the ultimate payoff, virtual reality and optimization. This is where we step into the matrix, so to speak, to test and perfect these designs mathematically.
So our mission today is to understand how engineers use this digital toolkit to save staggering amounts of time, money, and, let's be honest, their own sanity, all by simulating reality before they even think about cutting a piece of metal.
It's the journey from educated guessing to calculated perfection. It's a fascinating story.
It really is. So let's start at the beginning. Before the fancy software, before the VR goggles, you have to change how people think and work. Let's talk about concurrent engineering. The sources peg this as a phenomenon of the 1980s.
It was a huge phenomenon, and it grew out of a really serious problem. To understand it, you have to look at where it started, which, as is often the case with these big technological shifts, was in the U.S. Department of Defense.
The DoD, right. They have the complex projects and the budget to try and fix them.
Exactly. So in the 80s, the DoD is looking at its procurement process for these incredibly advanced defense systems, fighter jets, submarines, you name it. And they realized they have a fundamental systemic flaw.
Which was what?
The people designing the thing were completely disconnected from the people who had to actually build the thing.
The classic divide. The ivory tower designers versus the factory floor crew.
A chasm, really. You had brilliant engineers designing these systems to be aerodynamically perfect, theoretically flawless. But they weren't thinking at all about what the source calls manufacturability.
Can you actually build it?
Can you build it? Can you build it on time? Can you build it for a reasonable cost? The answer, too often, was no. A design would be finalized, signed off, and then it would hit the factory floor.
And that's where we get this term the source uses, factory shock.
It's a perfect term.
Yeah.
The design lands, and the manufacturing engineers look at it and just, their jaws drop. They see a part that requires 5-axis machining when a simple stamped piece would do, or a bolt that's placed in such a way that you'd need a child's hands and a custom-built wrench to tighten it.
So they're discovering these massive shortcomings, but it's way too late in the game.
Way too late. The tooling has been ordered, the materials are on their way, the production line is being set up. To go back and change the design at that point isn't just expensive, it's catastrophically expensive. It causes huge delays.
Okay, so the DoD sees this as a massive drain. This leads to a formal report from the Institute of Defense Analyses where they actually define this new idea.
They do. They give us the first real formal definition of concurrent engineering. And it's a bit of a mouthful, but the key words are right in there. They call it a systematic approach to the integrated concurrent design of products and their related processes.
Integrated and concurrent. Those are the magic words.
For everything. Concurrent just means at the same time. So instead of the old way, the classical mold of engineering.
Which was sequential. Step A, then you finish step A, then you start step B.
Exactly. Designer finishes, throws it over the wall to the manufacturing engineer. Manufacturing engineer figures out how to build it, then throws it over the wall to the quality control team. It's a relay race.
I love that over-the-wall imagery. It implies you don't even see the person you're handing off to. You just lob it over and hope for the best.
It's almost adversarial. But CE says, no, we're not doing that. The core idea is parallel working. From the absolute outset, from the first sketch on a napkin, you have everyone in the room.
Everyone.
Everyone. You don't just consider design. You consider all elements of the product's entire life cycle: quality, cost, the schedule, user requirements. And this is the one that really stood out to me from the sources, even disposal.
Right. I have that note highlighted too. The idea that in CE, the customer isn't just the person who buys the final product.
That's a huge mental shift. The customer is anyone downstream who has to interact with what you've made. The manufacturing team is your customer. They need a design that's easy to build. The maintenance crew is your customer.
So if you design a car engine where you have to remove 3 other components just to change an oil filter.
You've failed your maintenance customer, and that failure has real costs. It means higher repair bills, customer dissatisfaction, a damaged brand reputation, all because the designer didn't think about the person who'd have to service it 10 years down the line.
And that includes the disposal team, who has to figure out how to safely and efficiently recycle it at the end of its life.
Precisely. Are there toxic materials? Can it be easily disassembled? These are design questions in a CE framework.
But getting people who are used to working in their own little kingdoms to suddenly collaborate must have been challenging. You're talking about a major culture clash.
Oh, it was a huge battle. The sources talk about several major barriers. The first, obviously, is that over-the-wall mentality. It was just how things were done. It was comfortable.
But then there's something they call the cost paradox. This sounds like where the accountants get nervous.
This is where management gets very nervous. Because on paper, concurrent engineering looks more expensive upfront.
How so?
You need bigger teams from day one. You're having more meetings. You're paying a manufacturing expert, a quality assurance person, maybe even a materials disposal specialist to sit in on a conceptual design meeting.
And a manager looking at the quarterly budget just sees salaries and meeting room costs going up. It looks like waste.
It looks like pure inefficiency. Why are all these people here? The designers haven't even designed anything yet. But that's the paradox. You spend that money up front to save 10, 100 times that amount down the road.
Because you catch the untightenable bolt problem in the meeting, not after you've built 1,000,000 of them.
Exactly. You avoid those catastrophic factory shocks. You have far fewer engineering change orders late in the process, which are incredibly costly. The product gets to market faster, which is a huge competitive advantage. It's the ultimate measure twice, cut once.
There's another conflict mentioned, a more human one. The clash between command-style management and what they call team empowerment.
Yes, this is about power and control. Traditional engineering was very hierarchical. A senior engineer makes a decision, and it flows downward. CE requires a much flatter structure.
The sources describe the CE team as a flat entity, or maybe a 2-level structure with a leader and some sub-teams.
Right. It's not about command and control. It's about consensus and collaboration. Information flows horizontally between disciplines, not just up and down the chain of command. And that can be very threatening to old-school managers.
And also to old-school engineers, it seems. They talk about the clash between rigorous analysis and parallel work.
This is a deep-seated cultural thing for engineers. The classical training is all about rigorous step-by-step analysis. You don't move on to the next step until you have complete, verified, perfect data from the previous step.
You want certainty.
You crave certainty. But in CE, you can't have it. You're working in parallel. The team designing the chassis is working at the same time as the team designing the engine that goes in it.
So you're working with tentative data, incomplete information.
You have to. The engine team might say, okay, we think the engine block will be this size plus or minus 5%, and the chassis team has to take that incomplete data and start their design work.
That sounds terrifying for an engineer who likes precision.
It requires a massive amount of trust. It's a high-trust environment. You have to trust that your colleague in the other department will tell you the instant their data changes. If the engine designer realizes the block has to be 6% bigger, they can't sit on that information. They have to communicate it immediately.
Because if they don't, the chassis won't fit and the whole parallel process collapses.
It breaks down completely. The workflow is described as these long intervals of focused parallel work, punctuated by these short, intense bursts of communication to sync up and produce consensus.
Work, sync, work, sync. It's a rhythm.
It is. But for that rhythm to exist, you need more than just good intentions. You can't just throw people in a room and say, collaborate. You need the infrastructure. You need the technology to make it all happen.
Which is the perfect segue to our second pillar.
Yeah.
The infrastructure, the technologies of collaboration. How do you get all these different experts who might not even be in the same building talking to each other effectively?
Well, the sources give us a bit of a fun historical tour here. Starts with the basics.
Let me guess. Email.
Email. The source, written a while ago, notes that it had already been in use for a quarter century. But they talk about the move from just plain text to multimedia mail, being able to embed images and data.
And they mention a specific product that I have not heard in a very long time. Lotus Notes.
A true blast from the past. But you have to understand how groundbreaking that was. It wasn't just a messaging system. It was about creating structured, shared databases for communication.
So it's not just sending a message that gets lost in an inbox. It's contributing to a central pool of knowledge that everyone on the project can access and search.
Precisely. It's about creating a project memory.
But then things get even more interesting when we get to what the source calls computer-supported meetings.
This is where the Xerox Collab comes in. I was fascinated by this.
The Collab project at Xerox PAROX was so ahead of its time. They basically invented the concept of the electronic chalkboard.
And they had that great acronym for it. WASIWIS.
WASIWIS, what you see is what I see. It seems so obvious to us now. We do it every day on Zoom or Teams with screen sharing. But the idea that multiple people could be looking at a digital workspace, all seeing the exact same thing in real time, and all being able to interact with it, that was a game changer.
It absolutely was. It meant the design review meeting was no longer just people pointing at a physical blueprint. It became a dynamic, collaborative design session. But there were even more advanced tools.
The ones for argumentation, like ArgNoter and Shebus.
Right. These tools recognized a fundamental truth about engineering. It's a series of debates and decisions.
It's not just about drawing pretty pictures, it's about arguing over trade-offs.
Exactly. You have what the source calls a tiger team, this multidisciplinary group of experts. The material scientist says we should use composite. The manufacturing engineer says composite is too expensive to machine. The structural engineer says the alternative, aluminum, isn't strong enough. You have a conflict.
And these tools were designed to structure that argument.
Yes. Instead of it just being a heated discussion where important points get lost, these systems provided a framework. You formally propose an idea. Use composite. You then attach arguments for and against it. You document the final decision, and crucially, the rationale behind it.
The rationale. That connects back to what the source calls corporate history and memory.
This is one of the single biggest, most persistent problems in long-term engineering projects, the problem of lost rationale.
You've got a blueprint from 15 years ago, you're doing a redesign, and there's a weird bracket on it, and nobody, absolutely nobody in the building knows why it's there.
Exactly. The drawing shows you what it is, the geometry, but it doesn't tell you why. Was it there to solve a vibration issue that no longer exists? Was it to hold a sensor that was later removed? You don't know.
And because you don't know, you're afraid to remove it, because maybe it's critically important.
So you leave it in, adding unnecessary cost and weight to the new design, all because the original intent was lost. That's why they started developing electronic design notebooks, or EDNs.
To capture the thinking, not just the final geometry.
To capture the conversation, the trade-offs, the why. There's a brilliant example in the text about this. They talk about a system for constraint management and the ACID test for monitoring a project's health.
Another great acronym. Let's break down ACID.
It stands for Access, Choose, Interpret, and Display. For a project leader to manage a complex design, they need a system that lets them do 4 things. First, access all the relevant information, past and present.
Okay, get the data.
Second, choose the specific parameters they want to look at. You don't want to be flooded with everything. Third, and this is the key, interpret that information to understand what's really going on. And finally, display it in a way that's intuitive and easy to grasp.
And the specific example they used to illustrate this was about a jet engine blade, right? The strength constraint.
It's a perfect example. So imagine you're the project leader. You pull up your project dashboard. The system flags an alert. Blade strength constraint violated. Okay, that's the data, but it's not enough.
It's the what, not the why.
Exactly. A good system lets you click on that and interpret it. You dig deeper. And the system shows you who is violating the constraint. It's the aerodynamics engineer. And it shows you that he's done it 10 times in the last 2 days.
Okay, now it's getting interesting. It's not a random error. It's a pattern.
It's a pattern. And the electronic design notebook tells you why. The notes show that the aerodynamics engineer is relentlessly trying to tweak the blade shape to optimize the airflow path through the turbine.
He's not making a mistake. He's pushing the boundaries of his own discipline to improve performance, but it's putting him in conflict with the structural requirements.
Precisely. Now, as the project leader, you have full context. You don't just see an error. You see a design conflict between aerodynamics and structural integrity. You know exactly which two engineers you need to get in a room together to find a compromise. That is effective, data-driven management, and it's impossible without this kind of digital infrastructure.
That makes perfect sense. So we've got the philosophy of teamwork, concurrent engineering. We've got the digital infrastructure to let them talk. Now we need the canvas, the digital space where the design actually takes shape. Let's get into computer-aided design, CAD.
Right. And it's important to remember that CAD has been around in some form for a very long time. The source gives a nod to the SAGE air defense system way back in the 1950s.
Using light pens on big CRT screens. It looks primitive now, but that was the genesis.
It was. It established the fundamental connection that CAD is all about, linking the intuitive creativity of the human hand with the raw processing speed and precision of a computer. But modern CAD is so much more than just electronic drafting.
It's not just about replacing the pencil and T-square with a mouse and keyboard.
Not at all. It's about building an intelligent mathematical model of an object. To understand that, we have to look at how these systems actually model geometry. The earliest method was the wireframe model.
The skeleton approach.
Exactly. You're just defining the edges of an object. It's basically a 3D stick figure. The main advantage was that it was computationally simple. In an era of slow computers, that mattered a lot, but it had a massive, fatal flaw.
Ambiguity.
Ambiguity. If you look at a wireframe cube on a screen, your brain can sometimes flip it inside out. You can't definitively tell which face is the front and which is the back.
It's like one of those optical illusions.
It is, and for a computer, that's a disaster. If it doesn't know which surface is which, it can't calculate things like surface area, volume, or mass. It can't tell if two parts are interfering with each other. The model doesn't know it's a solid object. It just thinks it's a collection of lines in space.
So we needed a better way, which brings us to solid modeling.
Solid modeling. Now, the computer understands that this is a solid object with an inside and an outside. The source breaks this down into two main methods for creating these solids, CSG and BREP.
Let's start with CSG. That's constructive solid geometry. This is the one that feels like playing with digital building blocks.
That's the perfect analogy. You start with a set of simple, predefined shapes called primitives. Things like a cube, a cylinder, a sphere, a cone.
And you combine them using Boolean logic.
Yes, the same AND, or not logic that runs all of computers, but applied to geometry. The main operations are union, subtraction, and intersection.
So if I want to make a simple part, like a block with a hole through it.
You'd start with a cube primitive, then you'd create a cylinder primitive. You move the cylinder so it passes through the cube where you want the hole. Then you perform a subtraction operation, cube minus cylinder. The computer calculates the resulting geometry, and you're left with a block with a perfect hole in it.
It's like virtual machining. You're removing material.
Exactly. And union is just adding things together, fusing them into one part. Intersection gives you only the volume that two objects share. It's a very powerful and intuitive way to build many types of mechanical parts.
Okay, so that's CSG. What about the other method, BREP?
BREP stands for boundary representation. Instead of combining primitives, this method defines an object by explicitly describing its skin, or its boundary.
So you're defining all the faces, edges, and vertices.
Correct. You're essentially creating a mathematical description of the object's surface. It's a more complex data structure, but it's also more flexible. It can represent much more complex, free-form shapes, like the body of a car or the wing of an airplane, that would be very difficult to build out of simple cubes and cylinders.
So most modern CAD systems probably use a combination of both.
Yes. Many are hybrid systems. You might use CSG-like operations to create the basic form and then use BREP tools to add complex features like fillets and chamfers.
Now, the source gets into another important distinction, parametric versus variational modeling. This feels like the step where the model gets smart.
It is absolutely the step where the model gains intelligence. This is a huge leap beyond just being a static 3D shape. Let's talk about parametric modeling first. It's all about defining relationships and constraints between different parts of the geometry.
So it's not just a collection of lines and faces, it's a system of rules.
A system of equations, really. Think back to our block with a hole. In a dumb, solid model, if you make the block wider, the hole just stays where it was. It might not be in the center anymore.
Right. You'd have to manually move the hole to recenter it.
In a parametric system, you don't just place the hole. You define a rule.
Hmm.
The center of this hole must always be at the geometric center of this block's top face. That rule is stored as part of the model.
So now, if I make the block wider,
The computer automatically resolves the equations. It finds the new center of the face and moves the hole to match. The design intent, the hole is in the center, is preserved.
that's incredibly powerful. It saves so much rework.
It's fundamental to modern design. This concept is taken even further with what's called feature-based modeling. This is another layer of intelligence.
This is where we start thinking in terms of primitive shapes like cylinders and start thinking in terms of engineering features like holes.
Exactly. You don't tell the computer to subtract a cylinder. You use a hole command, and you can specify what kind of hole. Is it a through hole? A blind hole? Is it countersunk? Is it threaded?
And the computer understands the engineering meaning of those terms.
Yes. So if you place a through hole in a part, and you later make that part thicker, the hole automatically gets deeper to maintain its through nature. The model captures your design intent, not just the resulting geometry. It knows you wanted a hole that goes all the way through, no matter the thickness.
Okay, this is amazing stuff. But underneath all this intuitive, feature-based modeling, the computer's just crunching numbers. The source touches on the math behind the graphics, how the computer actually moves things around using matrix algebra.
It's worth a quick look because it's so fundamental. Every single point or vertex in your 3D model is stored in the computer's memory as a set of coordinates, an x, y, and z value.
So a simple cube might just be 8 sets of coordinates.
Right. And when you, the user, want to move that cube on the screen, the computer performs a matrix operation on all 8 of those coordinate sets simultaneously.
So let's take the simplest one, translation, just moving it.
That's basically just matrix addition. You define a translation matrix, which the source writes as T equals the matrix containing delta x and delta y. In 3D, it would have a delta z as well, and you just add that delta, that change, to the original coordinates of every point.
New position equals old position plus the change. Simple enough. What about scaling?
Scaling is matrix multiplication. You define a scaling matrix, S, and you multiply the coordinate matrix by S. The source shows this as I prime equals I multiplied by S. If your scaling factor is 2, all the coordinates get multiplied by 2, and the object doubles in size.
And rotation is the most complex one, I assume.
It is. The rotation matrix involves trigonometry signs and cosines to calculate the new coordinates as the object pivots around an axis. And the amazing part is that when you're smoothly spinning a complex model on your screen with your mouse, the computer is performing millions of these matrix multiplications every second.
It's incredible to think about the horsepower required, but all this complexity creates a problem. If I'm using brand XCAD software and you're using brand Y, how do we share these complex, intelligent models? The interoperability problem.
Well, it's a massive, persistent headache in the industry. For a long time, it was a huge barrier. You were locked into one vendor's ecosystem.
So standards had to be developed, neutral file formats.
Exactly. The source mentions a couple of key ones. The first big one was IGES, which stands for the Initial Graphics Exchange Specification. This was an early ANSI standard in the US.
And it was a good first step, but had its problems, right?
It did. IGES was pretty good at translating basic geometry surfaces and wireframes, but it often struggled with the complexities of solid models and could lose some of the intelligence. It could be ambiguous.
Which led to the development of STEP.
Right. STEP, the Standard for the Exchange of Product Model Data. This is the big international standard, an ISO standard. It was designed from the ground up to be much more robust. It's not just about transferring the shape. It's designed to transfer the full product model, including the parametric intelligence, feature information, and other metadata. It's the lingua franca of modern CAD.
Okay, so using all this tech, we've designed our part, we've collaborated on it with the whole team. It exists as a perfect, intelligent digital model. But now we want to know, does it work in the real world? But we're not ready to build it yet.
Now, we enter the simulation. We step inside the model. This brings us to our fourth pillar, virtual reality and engineering.
VR. The source has a great, simple definition. It calls it an oxymoron.
Reality that does not exist. It's a good way to think about it. But for an engineer, it's really defined by two key characteristics, immersion and interactivity.
Immersion is the feeling that you are in the digital world, not just looking at it on a screen.
And interactivity means that the world responds to you. When you move, your viewpoint changes. When you reach out and touch something, it reacts. Those two things together create the sense of presence that defines VR.
And to make that happen, you need some pretty specialized hardware. The source calls them the toys. Let's talk about the input devices first.
Right. How do you get your actions into the virtual world? The source gives a great nod to the Nintendo Power Glove, which many of our listeners might
That's
remember,
for the home enthusiasts.
for the home enthusiasts. But in a professional engineering lab, you'd be using something much more sophisticated, like the Cyber Glove. These are gloves lined with fiber optic cables or electrical sensors that can precisely track the bend of every joint in your fingers.
So your virtual hand can actually make a fist or point.
Exactly. Then you have tracking devices, like those from Ascension, that use magnetic or optical systems to track the position of your head and hands in 3D space. And they mention Spaceballs and 6 DOF mice.
6 DOF. 6 degrees of freedom.
That's right. It means it can track not just position left, right, up, down, forward, back, but also orientation, pitch, yaw, and roll. It gives you complete freedom of movement in a 3D space.
Okay, so that's how we get information in. What about getting it out? How do we see and feel this virtual world?
The most famous output device is the HMD, the head-mounted display, the big goggles that block out the real world and put screens right in front of your eyes.
That gives you total immersion, but the source notes, they often had drawbacks, like being heavy or having low resolution, especially the early ones.
They did. An alternative for desktop use is stereo glasses. These are shutter glasses that flicker, with each lens opening and closing in perfect sync with the monitor, which is displaying alternating images for your left and right eye. It tricks your brain into seeing a true 3D image popping out of the screen.
But the output device that just blew my mind was the haptic interface. They mentioned the Phantom device specifically.
Haptics is the science of touch, and this is where
Yeah.
VR gets really wild. The Phantom was an early robotic arm that you would hold, and it would provide force feedback.
So you can feel the virtual objects.
You can feel them. If you're moving your virtual hand and you push it against a virtual wall, the robotic arm will physically push back against your real hand. You can feel the shape, the texture, the resistance of an object that doesn't actually exist.
The applications for that in engineering are just staggering. You could test the ergonomics of a new dashboard design by actually feeling how far the reach is to the radio knob.
Or you could simulate a complex assembly task. Can a mechanic actually fit their hand and a wrench into this tight space to remove a part? With haptics, you don't have to guess. You can feel it.
So we have all this hardware, and the source says it gets configured into a few different types of VR systems.
Broadly, yes. You have the fully immersive systems. The classic example is the SAN-BE, which is a room where the walls, and sometimes the floor and ceiling, are rear projection screens. You stand in the middle, put on the glasses, and you are completely surrounded by the virtual world. Great for architectural walkthroughs or driver training simulations.
Then there's the other end of the spectrum, desktop VR.
Right. They call it a window on a world. This is much cheaper. You're using a standard computer monitor, but with stereo glasses to get the 3D effect. It's less immersive, but perfect for things like CAD model inspection.
And there are hybrids in between, like a virtual workbench where a 3D image is projected down onto a table.
So why do all this? Why invest in this expensive, complex technology? Is it just a cool gimmick?
I'm guessing the answer is money.
The answer is always money. It all comes back to a statistic mentioned in the source that is just eye-watering. 60 to 70% of a product's total lifecycle cost is committed and locked in as soon as the initial concept design is finalized.
Wow, let that sink in. By the time you have the basic shape and concept, most of the money has, in effect, already been spent.
Exactly.
Yeah.
Because that concept dictates the materials you'll use, the manufacturing processes you'll need, the complexity of assembly, everything. So if you make a mistake at that early stage, it's an incredibly expensive mistake.
And virtual prototyping is about catching those mistakes before you ever cut a single piece of metal.
That's the whole game. The source gives an example of a virtual lathe. You can put your digital part in a digital machine tool, program a digital cutting tool, and watch the simulation. You can see if the tool will chatter, if it will collide with the part holder, if the surface finish will be acceptable, all without wasting any material or machine time.
They also mention a system called converge, which sounds like something out of Star Trek.
The conceptual virtual design system. This was a research system where the designer could use voice commands and hand gestures inside a VR environment to create and manipulate shapes. Literally saying, computer, make that cylinder longer while stretching it with your hands.
So it's about making the design process more intuitive and catching those fundamental conceptual errors right at the very beginning where it's cheapest to fix them.
That's the billion-dollar idea right there.
Okay, so we simulated the world to see if our design is usable and buildable. But is it the best possible design? Is it the cheapest, the strongest, the most efficient? For that, we need to go beyond just simulation. We need to get into the brains of the operation.
This is our final segment, and it's where the heavy math lives. Design optimization.
What is the core concept here? What are we trying to do with optimization?
In short, optimization is a mathematical way to find the best solution from among an infinite number of possibilities without having to test them all.
Because testing them all would be impossible.
It would literally take longer than the age of the universe for any non-trivial problem. So, to do optimization, you need three things: a mathematical model of your system, a performance criterion you want to maximize or minimize, and a set of independent variables that you can change.
And the source gives us two fantastic, really concrete, real-world examples to show how this works. I want to walk through them. First up, the oxygen supply system for a steel mill.
A great classic systems engineering problem. You have a basic oxygen furnace in a steel plant, and it needs huge blasts of pure oxygen at specific times. The question is, how do you design the most cost-effective system to supply that oxygen?
And the system has three main components.
Right. You have an oxygen plant that actually produces the gas from the air, you have a big storage tank to hold it, and you have a compressor to pressurize the gas so you can fit a lot into the tank.
And right away, you can see the trade-offs.
It's all trade-offs. You could build a gigantic oxygen plant that can produce gas as fast as the furnace needs it. That way, you wouldn't need a big storage tank. But a huge plant has a massive upfront capital cost.
Okay, option two. You could build a much smaller, cheaper plant that just runs constantly, 204/7, slowly producing oxygen.
But if you do that, you need a massive storage tank to act as a buffer, to hold all that gas until the furnace needs a big blast of it. And a huge high-pressure tank is also very expensive.
And to get all that gas into the tank, you need a really powerful compressor, which is not only expensive to buy, but also costs a fortune in electricity to run.
Exactly. Every decision you make affects the cost of the other components. So the engineers defined the key variables they could play with: the production rate of the plant, which we can call F, the capacity of the tank, V, the capacity of the compressor, H, and the maximum storage pressure, P.
And then they wrote a giant equation for the total cost.
A cost function. This is the heart of the optimization. The source describes the annual cost equation, and it's basically just adding up all the different costs. You have the plant cost, which is some fixed cost, A1, plus a variable cost that depends on the production rate, A2 times F.
So A1 plus A2 times F.
Then you add the tank cost. The source notes that the cost of pressure vessels often scales with volume raised to some power, so they model it as B1 times V raised to the power of B2.
Okay, so a term for the plant, a term for the tank.
Then a term for the compressor, which is similar, B 3 times H raised to the power of B4. And finally, you have to add the operating cost, the electricity, to run that compressor. That's a term like N times B 5 times T1 times H.
So you have this big, long equation that adds up the cost of the plant, the tank, the compressor, and the power. And the goal is to find the specific values for F, V, H, and P that make the result of that equation as small as possible.
That's it. You feed that equation and the variables into an optimization algorithm, and the computer crunches the numbers. It will methodically test different combinations, always moving in the direction of lower cost, until it finds the sweet spot, the optimal balance between all those competing factors.
It's amazing. It turns a complex design problem into a solvable math problem. The second example is the welded beam, which feels much more like a classic mechanical design scenario.
It is. This is a problem every mechanical engineering student has probably seen in some form. You have a steel beam that's welded to a rigid support, and it needs to hold a 6,000-pound load at its end.
And the goal is simple: minimize the cost.
Minimize the total cost, which is the cost of the material used, plus the cost of the labor to weld it.
So what are the variables we can change here?
There are 4 design variables: the thickness of the weld, H, the length of the weld, L, the thickness of the beam itself, T, and the width of the beam, B.
And just like before, there's a cost function.
Yep. The source lays it out. F of X equals. Well, there are 2 terms for the weld. The first is H squared times L, which is related to the cost of the weld material. Then you add C, 3 times H squared times L, which is the labor cost, with C3 being a cost coefficient.
Okay, so material and labor for the weld.
And then you add the cost of the beam itself, which is C4 times T times B, multiplied by the sum of L plus L. That just represents the cost of the steel bar stock.
But wait, if that's the equation, the cheapest solution would be to make H, L, T, and B all equal to 0. Just use no material.
But you can't, because you have rules you're not allowed to break. These are the constraints. This is the most important part of real-world optimization.
The design has to actually work. It can't break.
It has to be safe. So the engineers add several constraint equations. First, the shear stress in the weld, which we'll call tau, cannot be greater than the maximum allowable design shear stress for that material, COD.
So the weld can't rip apart.
Second, the bending stress in the beam, sigma, cannot exceed the maximum allowable normal stress, sigma. The beam itself can't snap. Third, the beam can't be so long and skinny that it buckles under the load. So the buckling load, PC, has to be greater than the applied load.
So the optimization algorithm has to find the cheapest combination of H, L, T, and B that satisfies all of those safety constraints simultaneously.
Precisely. And the source notes that calculating those stresses, particularly the shear stress in the weld, tau of x, is not trivial. It's a combination of a primary shear stress, tau prime, and a secondary torsional stress, tau double prime. Some fairly heavy math.
But the beauty is, the engineer doesn't have to solve it by hand 1,000 times. The computer does the hard work. It explores the design space, constantly checking, is this design cheaper? Yes. Is it safe? No. Okay, back up. Is this design safe? Yes. Is it cheap? Not really. Let's try to make it a little thinner.
Until it finds the design that is right on the edge of the allowable limits. The absolute cheapest, lightest beam that will do the job safely. That's the power of optimization.
But what if you have goals that are in direct conflict with each other? The source brings up a final concept here. Goal programming.
This is a really interesting and practical area. It's for situations where you have multiple competing objectives. The classic example they give is from machining.
You want to maximize your metal removal rate. You want to cut the part as fast as possible to make more parts per hour.
But you also want to maximize your tool life. You don't want to be constantly stopping the machine to replace a worn-out drill bit because that costs time and money too.
And those two goals are in direct opposition. The faster you cut, the hotter the tool gets, and the faster it wears out.
You cannot have the absolute maximum of both at the same time. It's impossible. So goal programming changes the question. Instead of trying to maximize both, you set goals. Say, my goal is a metal removal rate of X, and my goal is a tool life of Y.
And then you try to get as close as possible to those goals.
Exactly. The mathematics is set up to minimize the deviations, the underachievements or overachievements from those goals. These are often written as D- and D+. You're trying to find the solution that has the smallest total disappointment.
I like that. You're mathematically minimizing the engineer's disappointment.
Right.
A very elegant way to solve a very real problem.
It is. It's a pragmatic way to handle the messy reality of conflicting requirements.
So if we take a step back and look at the whole journey we've been on today, it's really quite incredible. We started with the old world, the over-the-wall philosophy where everyone worked in isolation.
Then we saw the rise of a new philosophy, concurrent engineering, focused on teamwork and a life cycle view.
We looked at the digital glue that held those teams together, the communication and coordination technologies. We moved to the digital canvas of CAD, where we learned to build intelligent models instead of just dumb drawings.
From there, we stepped inside those models with virtual reality to test them in a human-centric way. And finally, we used the pure logic of design optimization to mathematically perfect them.
It paints a clear picture. Modern engineering is not just about physics and materials anymore. It's about information management, it's about simulation, and it's about applied mathematical logic. The wrench and the hammer are still essential, but they're now guided by this immense mountain of data and computation.
The physical act of making something is now the final step in a very long, very deep digital process.
It is. And that brings me to a final provocative thought for you to take with you. We've talked all about this incredible power of simulation. Virtual prototyping, mathematical optimization, having a perfect digital memory of every decision. But are we in danger of optimizing away the happy accidents?
That's a really interesting question. What do you mean?
Well, so many great inventions in history came from mistakes, from serendipity. Someone tried something that shouldn't have worked or mixed the wrong things together and discovered something amazing like penicillin or Post-it notes. If we only ever build what the computer has already confirmed is the most efficient or optimal solution.
Do we lose the opportunity for those unexpected breakthroughs?
Exactly. If we only ever cut the metal that the simulation says is perfect, do we lose the chance to discover something new from a design that looks wrong on paper, but has some unforeseen benefit in the messy, unpredictable real world? Are we designing ourselves into a perfectly efficient box and losing the random spark of true invention?
It's the paradox of perfection. If you eliminate all risk and error, you might also eliminate all surprise.
Something to think about. Well, that brings our deep dive into the digital transformation of engineering to a close. This was a fantastic journey.
It was a pleasure, as always.
And remember, if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.